Hey guys, this is Dr. Thomas. This is my first content video for Chem 1212. I'm starting in chapter 11. I'm following the PowerPoint that you should be able to find in either D2L or on the shared class files. Either of those places should be updated. Chapter 11, there's a lot of material from 1211 that you should remember before you start into this chapter. You're going to need to remember how to draw Lewis dot structures, determine whether molecules are polar or nonpolar. We're going to do calculations involving heat, which Lewis dot structures is chapter 8 and 9 from 1211. Heat calculations are chapter 5. Of course, you're going to need naming compounds from chapter 2. You're going to need mole calculations from chapter 3 and 4. So there's a ton of information you need to be reviewing as we go. I know in the first week of class we do a little bit of that work, but to do this chapter well, you really have to have that information at hand and ready to go. Okay, so anyway, kinetic theory of matter. So chapter 11 is all about liquids. Now we'll say at the end of 1211 we did a chapter 10 was about gases. Now we're doing a chapter about liquids. Chapter 12 will be about solids, and then chapter 13 will be about solutions again. So we're talking about all the different physical states that matter can exist in. The beginning of this chapter focuses on how do we know which physical state a given substance is going to be on. So that's going to introduce the concept of intermolecular forces. So that's kind of where we are in our setup. So the physical state of a substance is going to be related to its kinetic energy. If you remember, kinetic energy is the energy of motion. So the more the particles are moving, that's going to shift them more towards a gaseous state. And if the molecules are not moving very much or holding pretty still, that's going to tend to put us in more of a solid state. Okay. So the beginning of the chapter talks about kinetic theory, how particles interact with each other. Essentially, the big thing about this is that the interaction of particles, whether they're attracted to each other or repelled by each other, tends to be based on charge, which a fancy word for attractions related to charge is called electrostatic interactions. So in physics, we would have used this equation if we were talking about electrostatics and charges, where basically the force of attraction between two particles is related to C as a constant, but Q1 and Q2 would represent the charges of two particles. If we're talking about the force of attraction, the two charges have to be opposite, where one charge is positive, the other charge is negative, because we know that opposite charges attract. If you had two charges that are the same, then it would be a force of repulsion instead of attraction. Okay, but from this equation, we should be able to see that two things are important. Q1 and Q2, the charges. The larger the charges, the greater the force of attraction between the particles. So if particles have, assuming they're opposite charges, if the charge is a small value, that's going to give us a weak force of attraction. And if the charge increases, then the force of attraction will also increase. Okay. Also, we have the radius squared in the bottom of the equation. So that should tell us that for the force of attraction between charged particles, the distance between the atoms, if I have two atoms, the radius of each atom is related to the distance between them. So the radius between the two atoms, if it increases, then again, that's going to decrease the force of attraction that we have in the particles. So this equation is going to be very important in all of the intermolecular forces that we're going to talk about later, although we're going to explore them qualitatively, so we're not actually going to do any math with this equation. It's just important to be aware that it exists and that it relates to what we're talking about. So as we talk about kinetic energy, of course, the best way for us to measure or represent the kinetic energy is to use temperature. Temperature is a measurement of the average kinetic energy of particles. We have three temperature scales, of course: Fahrenheit, Celsius, Kelvin. We really never use Fahrenheit in science. When we use Celsius, we can use that for comparing temperatures to some degree, but really Kelvin, of course, is our best scale. So Kelvin is called the absolute temperature scale. It relates directly to the average kinetic energy of the particles. So if you double the kinetic energy of the particles, the temperature in Kelvin actually doubles. Okay, that is not true in the other scales. So that is why the preferred temperature scale is always going to be Kelvin. And then there are other assumptions that when molecules bump into each other, or atoms or ions or whatever, that when they bump into each other, the collisions are elastic, which means energy is conserved. When we're talking about the interaction of particles in terms of physical states, we're assuming there's no chemical reactions that occur, blah, blah, blah. There's a lot of assumptions that go on, so just read through that section to be aware of it. Also, as we go through these sections, you have to have some awareness of the physical states and their general properties. Gases have the lowest density because the particles are far apart. Liquids and solids are called the condensed phases because all the particles are close together. They're interacting a lot more. A lot of this information, again, you should know it from 1211. You should review and have a good idea of all these things. When I do these videos of the lecture, the things that you can pick up from in reading, I'm going to skip over, okay? I'm going to try to focus more on the things that you guys need to know that are a little bit harder to pick up. I'm also going to try to make sure that you have a clear idea of what we expect you to know. So, first of all, if we're going to talk about the interaction between particles, we have to distinguish the difference between what we call an intramolecular force and an intermolecular force, okay? Intra, the prefix intra means within. So an intramolecular force, if I look at an HCl molecule, the bond that holds the hydrogen and the chlorine together, that covalent bond right there, that is an intramolecular force. It's the force between the atoms inside the molecule that keeps them together. Those covalent bonds are extremely strong. Takes 431 kilojoules per mole to break that bond. Okay, when we are normally just heating a sample up and cooling it down, there's not enough energy involved in that process, typically, to break a covalent bond. Okay, so that is not what we're going to be focused on in this chapter. Really, we learned about covalent bonds in 1211 when we did Lewis dot structures and all that kind of stuff. What we're going to be focused on instead are intermolecular forces, which are the forces that are between two separate particles. Now, each particle could be a molecule of HCl. It could be a bigger molecule, like a gasoline molecule or a sugar molecule, or it could be a single atom, or it could be an ion like chloride, or it could be a polyatomic ion like nitrate. Okay, all of those are particles. So in this case, I'm going to compare one particle of HCl and another particle of HCl, and I'm going to study how they interact with each other. Okay, now, the attractive force between these two molecules is about 16 kilojoules per mole, which is a much smaller value than the intramolecular force we talked about earlier. So if I have liquid HCl and I heat it up until it boils, the force that's going to break is going to be this force, which means the molecules can move apart from each other, and that would turn the liquid into the gas. We're not going to study at this chapter anything about breaking the covalent bonds, because we're talking about physical changes here, not chemical reactions. So when we look at the three physical states, solids, basically what we have there, if in a solid, the particles in the substance are close together, there's a strong interaction between them. If there's a strong interaction, what that means is there's a strong intermolecular force holding the particles together. Specifically, the intermolecular attractions are going to be a lot stronger than the kinetic energy of the particles. If you remember the kinetic energy of the particles, that's the energy that makes the molecules want to move. And if the movement of the molecules is strong enough to exceed the intermolecular forces, then that means that they're not going to hold in place, which in a solid, all the particles are going to stay relatively still. So, in a solid, we have a relatively low kinetic energy compared to the intermolecular attractions. So the intermolecular forces dominate, the particles are held in place, they're held together, there's a strong attraction. That's what a solid is. If we move to a liquid, now the intermolecular forces and the kinetic energy are kind of on the same level, so that the kinetic energy is enough to make the molecules move around a little bit, but the intermolecular forces are still strong enough that they can't get away. So what happens is at this point, the particles or molecules, they don't stay still, they move around, but they're still close. Okay? So they're on probably the same order of magnitude for those two values, and that keeps them in a balance with each other. That's what a liquid is. So the kinetic energy has increased some compared to a solid, and some of the intermolecular forces might be starting to break a little bit, but they haven't fully released the molecules to fly away from each other. Then finally we have gases. This is where now if I've raised the temperature to the point where a substance turns into a gas, now the kinetic energy is significantly higher than intermolecular forces. At that point, the energy making the molecules move is so strong that the intermolecular forces are broken, they're completely disrupted, and the molecules move freely. That's where they just fly away and they will expand to fill up whatever container they're in. That's the gaseous state. Okay. Again, solid, liquid, gas. There are some descriptions of the general properties and a description of how everything exists in there. That's important information that you should take a look at. All that is in the book. So again, this slide is kind of a repeat of the same thing. Again, I'm just going to skim over it because I don't want these videos to be too long. So why do we study, like when I have on the slide IMF, that's an intermolecular force. So why are we studying intermolecular forces? Well, essentially, if we want to learn about why molecules behave the way they do, why does one compound exist as a solid at room temperature while another molecule exists as a gas or a liquid at room temperature? Okay, so if we want to be able to predict the physical state of a compound and the relative melting point and boiling point, like compare two compounds and figure out which one has a higher melting point than the other one, or if they're liquids, which one has a higher boiling point than the other one. That's something that we can do with intermolecular forces. We can also predict solubility, which compounds we think would be soluble in water versus being soluble in gasoline or hexane or something like that. So we have those comparisons that we can make. It also helps explain water is a very special molecule. On Earth, 70% of the surface of the Earth is covered by water. Why is water? It's a small molecule. Most small molecules of the size of water exist as gases. Why is water different from that? Why is the specific heat of water so much higher than other liquids? Blah, blah, blah. There's just a lot of properties about water that can be explained based on intermolecular forces. And then finally, there are other classes of important molecules where if we understand the intermolecular forces, it's going to help us understand in other branches of science why molecules behave the way they do. Big example of that, if you take biology, when you study DNA and you want to know, like, why does DNA, when it forms a double strand, why does adenine always bond with thymine and guanine always bonds with cytosine when it pairs up? Also, why does it form a double helix as it coils and everything? Those are things that can be explained based on intermolecular forces. So, here we go. We have a list. There are 4 intermolecular forces that we're going to talk about. They are ranked on this slide, and in terms of increasing strength or increasing energy. When I say increasing energy, I'm talking about how strongly they're attracted and specifically how much energy it takes to break them apart. Okay? So the highest one that we're not going to really focus on too much in this chapter, ionic attractions. If I have sodium chloride, basically each particle is an ion. So I'm going to have 2 different particles in that substance. There's the sodium cations and there's the chloride anions. The attraction between those particles is so strong that generally for ionic compounds, we can say that at room temperature, they are always going to be in the solid form. Okay, the force of attraction is so strong that at room temperature, the particles are not going to be able to get away from each other. And they're very rigidly locked in place. They form a crystal. There's very little movement of particles in the solid form. All right, so ionic attractions are going to be far and away number 1. We've already talked about ionic compounds. We've established here that they're going to be the highest. And then the other 3 are going to be the new ones that we're going to focus on for the most part in this chapter. Okay, now, why are ionic compounds the highest and these other ones are going to be much lower? Is the difference between, if you remember the equation we showed earlier, the force equals C times the 2 charge values over the radius squared. Ionic attractions have full charges. So sodium chloride has a +1 and a -1. If I look at like calcium sulfate, that's a +2 and a -2. Those are whole charges. If we have whole number charges, that's a much higher value of charge and force of attraction than these other molecules down here. These are going to be covalent molecules, and covalent molecules, at best, if they're polar molecules, they're going to have partial charges. A partial charge is going to be a much smaller amount of charge present in the molecule than having the complete charges. So it's a very significant gap between these. So anytime later on in this PowerPoint, I'm going to give a list of compounds, and you're going to have to rank them from lowest boiling point to highest boiling point or whatever. Ionic compounds are always going to be at the top of the list. Okay? And then beneath that, we're going to rank our 3 other forces: hydrogen bonding, dipole-dipole, and London forces or dispersion forces. Different books use different names for those, okay? So, and all 3 of these are classifications of van der Waals forces. But I'm going to cut off this video. I'm going to start on the next slide with the next video to talk about each of these and let you know what you need to know.